Hi there, welcome. This video is on using L'Hopital's rule to find certain kinds of limits, specifically limits of fractions that look like an indeterminate form. I'll explain that vocabulary in a minute. This is on section 4.4. So first of all, let's just explain what L'Hopital's rule is. And so I have this little explanation on the lecture notes. L'Hopital's rule is a method for simplifying certain kinds of limits. Specifically, if you have a fraction, some function divided by some function, the limit can be anything x going to a, but when you plug in that a value into the top and the bottom, you get 0 divided by 0. And that is called an indeterminate form. And there are several kinds. There are 7 kinds of indeterminate forms. And I'll show you what those 7 are. One more important thing is that the derivative on the top and the derivative on the bottom. So we're not doing quotient rule here. We're doing the limit of the derivative of the top part, the derivative of the bottom part, and that actually exists. So if you have a 0 over 0 form of a limit, and the derivative of the top part divided by the derivative of the bottom part has a limit that actually exists, then we know that this limit of the derivative of the top over the derivative of the bottom is the same as the original limit of f of x over g of x. So that's the idea of L'Hopital's rule. It can be used to simplify functions quite a bit in order for us to find the limit using direct substitution. By the way, we know L'Hopital's rule works because we recently did local linearization, saying that if you have a function and you look at it, at a very microscopic level, like super zoomed in, what you find is that the function is indistinguishable from a line. So you essentially have one function over another function, but the top function microscopically is just a line. I'll say mx plus b, but I'll use 1 because we're going to have another mx plus b. G of x will be some other mx plus b. So microscopically, like zoomed in a very, very small location. These lines are indistinguishable. These functions are indistinguishable from lines. But if you take the limit as x approaches, let's say 0 for these, I'll just make it easier to explain. This ends up being just m1 over m2. You figured this out in several previous homework assignments. You can divide top and bottom by x, or you can use a table if you like, but they end up just being the slopes, which are the derivatives, right? So the derivative of the top, the derivative of the bottom is what you end up with because of local linearization. All right, a little bit justification that might not be necessary, but might be interesting for some folks. All right, so by using a substitution, by like doing a change of variables, 0 over 0 can look exactly like infinity over infinity. So we say that L'Hopital's rule can also be used if it's infinity over infinity. So we still differentiate the top, differentiate the bottom, and still get the correct result. And in fact, there are several indeterminate forms. 0 times infinity. So if you plug in a number and it's not a fraction, but it's a thing times a thing, f of x times g of x, where f of x is 0 and g of x is infinity, or you can switch those two. That's also an indeterminate form. And you can use algebra to simplify this thing into either 0 over 0 or infinity over infinity. So this can be simplified into 0 over 0 or infinity over infinity. So we'd have to simplify it first so we can actually use the L'Hopital's rule. But we know ahead of time that these list of 7 things, or I guess it's more than 7 now, but originally I had 7 and then I lost count. Okay, sorry about that. Anyway, this short list of things are all simplifiable into 0 over 0 or infinity over infinity. And I have a list here. I don't need to read them all out to you. But those are the ones that we call indeterminate forms. And I tried to list them kind of in the order that we use them most frequently. So anyway, we'll see some examples of simplifying these into our 0 over 0 or infinity over infinity indeterminate form and then applying L'Hopital's rule. Now, I do list here on the bottom here, I do list a bunch of things which sometimes students think are indeterminate forms, but they are not. They are definitely determinate forms. So what do I mean by determinate? It means that we know what they are without actually doing anything. So I'm talking about a limit where, for example, the top part goes to 0 and the bottom part goes to infinity. You can think about the fact that 0 over any number, like 0 over 10 or 0 over 1,000, 0 over any number is going to equal 0. So the fact that the top part is 0 tells you that the result should be 0. And the fact that the bottom part is a large number, I mean, I'll change the top part to 7 or something over infinity, right? 7 over infinity is going to be 0 or 4 or 700. It doesn't matter what the top is. Anything divided by infinity is going to be 0. So we know 0 divided by infinity is always going to end up being 0, no matter what. So it's not something you need to try to simplify. It is a determinate form, and the result is going to be 0. Now, I am going to write out what these are, but it's kind of really nice if you don't memorize this list or try to write it down and reference it, because all of these should be reasoned out. Anything divided by 0 is either going to be plus or minus infinity. Plus or minus infinity times infinity is still plus or minus infinity. So this next one's plus or minus infinity. Something infinity times something that's infinity. Infinity times infinity is infinity. Infinity raised to infinity, that's just even more infinities being multiplied. Infinity to the 1, a lot of people might think, why is infinity to the 1 there? Because isn't that obviously infinity? Yes, but notice that 1 to the infinity, which is kind of similar, is actually indeterminate. 1 to the infinity could end up being 1, or it could be end up being 0 or undefined or anything else, right? So we don't really know what 1 to the infinity is. It is indeterminate form. However, infinity to the 1 is just one copy of infinity, and it's definitely equal to infinity. If you have any number divided by 0, as I mentioned before, any number divided by 0 is some version of infinity. Any number divided by infinity is going to be 0. 0 divided by any number is 0. And infinity divided by any number that's not 0, like 2 or 3 or something, is going to be infinity. It's actually plus or minus infinity, because b could be a negative number as well. So anyway, so those are our determinate forms. I just list them so that you can kind of get an idea of L'Hopital's rule doesn't work on everything. It works on some very specific things. There are 7 main ones, and I listed a few others that are not so common. So whatever the small number of things are, they are indeterminate forms, and those are worth writing down to make sure you know what they are. And then everything else should be determinate, so we should know what it is. All right, so let's see some examples, because I've been talking way too much about what's going on here. All right, so I'll just start off with some examples here. All right, so example A, I have the limit as x approaches 1 of ln x divided by x minus 1, so the function divided by a function. And the immediate thing I try is direct substitution. So I'm going to see what this is equal to. So this becomes ln of 1 divided by 1 minus 1. Right, just by substituting directly x into that expression. So if you remember your pre-calculus, or if you have a calculator handy, you'll know that ln of 1 is 0 and 1 minus 1 is 0. So we can use L'Hopital's rule. Right, 0 over 0, indeterminate form. So we can use L'Hopital's rule. So I'm going to say equals. I'm going to put a little LH here just to remind my readers that I'm using L'Hopital's rule to simplify this thing. And so I get a new, or I guess the limit carries forward. And then I differentiate the top and I differentiate the bottom separately. Again, it's not a quotient rule. I'm not like doing some wild thing. I'm just differentiating the top and I'm just differentiating the bottom separately. I know it seems a little strange because, we're supposed to use a quotient rule, but we're not trying to differentiate the function. We're just trying to find the local linearization of the top and the local linearization of the bottom. So we just need the derivative of those two things separately. All right, well, the derivative of ln x, if you recall, that's 1 over x. And the derivative of x minus 1 is 1 minus 0. So we end up with a limit as x approaches 1 of 1 over x over 1. And now I plug in 1. That becomes 1 over 1 over 1. And 1 over 1 over 1 is equal to 1. So since we know that this derivative version of the limit is equal to 1, we now know the original limit is also equal to 1. So this original limit that we were asked to find goes to 1 because of the fact that the derivative of the top, derivative of the bottom has a limit that exists. That means those two are the same. So that's the nature of how L'Hopital's rule works. That's pretty much every L'Hopital's rule problem. You do some direct substitution. You see if it's an indeterminate form. If it is, you do L'Hopital's rule, derivative of the top, derivative of the bottom. And then you figure out what that limit is. And if it exists, then you know the original limit is the same. Now, these problems do get more complicated because there's some more algebra involved in terms of simplifying it. There's some more, more complicated derivatives. And sometimes we may have to do more than just apply L'Hopital's rule. So let me show you some more complicated examples. But the gist is L'Hopital's rule is always the same process. Direct substitution to check if it's indeterminate. If it's indeterminate, use L'Hopital's rule, and then you get your limit, which is equivalent to the previous limit. Okay, let's see another example. All right, so I have the second example, B. I have ln x over x minus 1. This time x is going to 0. So the first thing I do is I try direct substitution. I get ln of 0 over 0 minus 1. ln of 0, again, you might have to use maybe a table of values by plugging in values that are close to 0. This should be 0 from the right, not 0 in general. I forgot to put a little plus sign there. So maybe things like 0.001 or 0.00001 or things like that. Or you could use a graph, or you could remember that the natural log of 0 is negative infinity. So this goes to negative infinity over negative 1. And that is not an indeterminate form. If I take infinity and divide by 1, I get infinity. So this is infinity, and there is nothing else you need to do. Right? You're all set. You're all set. Let's see. Yeah. Okay. So let's do part C. Part C, we have a limit. So let's go ahead and substitute in and see what we get. So let me try this in a different color. So I get 0 cubed plus 0 squared over e to the 0 minus 0 minus 1. So what does that become? Well, the top is definitely 0. E to the 0 is 1, so 1 minus 0 minus 1, so we get 0 over 0. So because we have 0 over 0, we can use L'Hopital's rule. So I will say we're going to use L'Hopital's rule. And I carry forward the same limit. You do have to keep writing the limit every time. You can't just ignore it. Unfortunately, you'll lose points because I'm required from the math union to take off points if you forgot to write the limit. So don't get me in trouble. Just remember to write the limit. All right, 3x squared plus 2x is the derivative of the top part of the function. And the bottom part, derivative of e to the x is e to the x, and then we have minus 1. Okay, so this limit, as long as it exists, is equivalent to the original limit. So let's find out what happens when you plug in 0. So you plug in 0, you get, you get 0 plus 0. I guess we get, 3 0 squared plus 2 times 0, right? I mean, it's going to be 0. The bottom part, we get e to the x, which is e to the 0 minus 1. So what is this? Well, the top part is 0. And the bottom part, e to the 0 is 1. So that's 1 minus 1, so it equals 0 over 0. So it appears at first glance that the L'Hopital's rule didn't get us anywhere. We still have 0 over 0. However, we have a different function that we're looking at in terms of the limit. We have this new version, which hopefully is simpler than the original version, and you can be the judge of that. But I think a lot of people might say that the exponents are lower and there's fewer terms on the bottom. So we essentially have something which might be an easier version or an easier form of this derivative. And it's still 0 over 0. It still is an indeterminate form. And if it's an indeterminate form, that means we can use L'Hopital's rule. And you mean, well, can we use it again? L'Hopital's rule doesn't, have any requirements about using it. Just says it has to be 0 over 0, right? And it is 0 over 0. So we can use L'Hopital's rule again. So I'll go up here a little bit. L'Hopital's rule on this second guy. So I still have the limit as x approaches 0. And the top, I have the derivative of the top, derivative of 3x squared and the derivative of 2x, and the bottom I have the derivative of e to the x minus 1. So I just applied L'Hopital's rule a second time. And then what do? Well, I see if I can find the limit. And one of the easiest ways is by using direct substitution. So what does this become? This x is going to 0, so I get 0 plus 2 over e to the 0. I guess technically 6 times 0 plus 2, but that is going to be 0. 6 times 0 is 0 plus 2, which is 2. E to the 0 is 1. And yes, we do get a limit that exists. So the limit of this sort of, second version of L'Hopital's rule is equal to 2. That means the limit of the first version of L'Hopital's rule is equal to 2, which means the limit of this original function right here is equal to 2. So that's how we can use L'Hopital's rule in more complicated situations. In this case, just using it multiple times. All right, some more examples. Example D I have here. It has the limit as x goes to infinity. So we're going to first plug it in. Now, many mathematicians will write this and put like a caveat, like this is not really what's going on. And I'll do the same thing, right? You can't really plug in infinity. But, our human minds can sort of figure out what's going on here if we do put that symbol in there. E to the infinity is e to some very, very large number. Again, from pre-calculus, you might know that this is equal to infinity, and infinity cubed, infinity times infinity times infinity, is equal to infinity. And so this is infinity divided by infinity. And infinity divided by infinity is equivalent to 0 divided by 0. And so we can apply L'Hopital's rule. It's our second form of L'Hopital's rule that we can use. All right, so let's do it. I'm going to loop it up. Derivative of the top. Oh, I got to write my limit again. Derivative of the top is e to the x. Derivative of the bottom is 3x squared. And this again goes to infinity over infinity. So I'm going to use L'Hopital's rule again. And I get the limit as x goes to infinity. Derivative of the top, derivative of the bottom. And this is still going to infinity over infinity. E to the infinity is infinity. 6 times infinity is infinity. So I'm going to apply L'Hopital's rule a third time. I get the limit as x approaches infinity. Derivative of e to the x is still e to the x. Derivative of 6x is 6. And this goes to infinity over 6, which is equal to infinity. So we had to apply L'Hopital's rule 3 times there. All right, just remind folks that anytime you're feeling like you get the idea of how these work, it's a great time to pause the video and try some of them yourselves. So this is a little reminder to maybe try some of these. And I'm gonna invite you to do so and then show you my solutions for these guys. Okay, well, if you tried that, fantastic. Welcome back. And if you're still watching, that's great. I'll show you some more of these, and hopefully that'll help you feel more confident to try them yourself. All right, so once again, I got to plug in the value. I'm going to plug in 2. So I get 2 cubed minus 7 times 2 squared plus 10 times 2 over 2 squared plus 2 minus 6. All right, so I get a little arithmetic here. I get, this is a 7. I get 2 cubed is 8. 7 times 4 is 28. And then that's plus 20. So the top part is definitely 0. 8 minus 28 is negative 20. Plus 20 is 0. What about the bottom part here? We get 2 squared is 4. 4 plus 2 minus 6 is definitely 0 as well. So we can use L'Hopital's rule because it is the indeterminate form of 0 divided by 0. Okay, so let's lope it up. Let's see if I can make this look nicer. Okay. Well, maybe not nicer is the word, but it is what it is. So I'll differentiate the top part. Differentiate the bottom part. And I will once again, oh, I forgot my limit thing, didn't I? Okay, so let me fix that. I have to write the limit each time. Limit x approaches 2. All right. So now I got to plug in my 2's. I get 3 times 2 squared minus 14 times 2 plus 10 over 2 times 2 plus 1. So what do I get here? I get 3 times 4 is 12. 14 times 2 is 28 plus 10 over 4 plus 1 is 5. Oh, this is not going to be 0 over 0. So this is good. It means I don't need to worry about using L'Hopital's rule again. 12 minus 28 is negative 16 plus 10 is negative 6. So negative 6 over 5. So our original limit, this crazy fraction thing up here, has a limit of negative 6 over 5. And we found that using L'Hopital's rule. All right. Next one, F. Let me just start by plugging stuff in. ln of infinity, I guess quotation marks, because you can't really plug in infinity, but we're doing ln of a very, very large number. And then we do infinity squared. Again, in quotation marks, because we can't really plug infinity. However, ln of a very large number, if you remember your pre-calculus, you remember the graph, or you could just plug in numbers into a table to figure this out yourself. You'd plug in a million, a trillion, and bigger, and you get infinity on the top, positive infinity on the top. Infinity squared is positive infinity on the bottom. You get infinity divided by infinity. It could be infinity divided by negative infinity. It could be negative infinity divided by, the signs don't matter. As long as it's some version of infinity over infinity, you can use L'Hopital's rule. Okay, let's do it. All right, so I got differentiate ln x, which is 1 over x, and I differentiate x squared, which is 2x. And then I'm going to plug in my infinity thing. So I get 1 over infinity on the top, and I get 2 times infinity on the bottom. Well, 1 divided by infinity, 1 divided by a very large number, 1 over a million, 1 millionth, or 1 over a trillion, 1 trillionth, that tends to 0. And 2 times infinity, well, that's just twice infinity, which is still infinity. 0 divided by infinity is not in indeterminate form. So you may not use L'Hopital's rule and get a correct answer. I mean, you can use L'Hopital's rule, but it'll give you a wrong answer. So we cannot use L'Hopital's rule. In fact, this is a determinate form. We know what this is equal to. 0 divided by infinity, in fact, is 0. 0, large number is 0. And any number divided by infinity is 0. So this is going to tend to 0. So we know the original limit. I'll write this time again. So the original limit of this function thing goes to 0. All right, well, I'm going to show you some algebraic simplifications of how to convert things that don't look like 0 over 0, but are still indeterminate, into things we can use L'Hopital's rule in. But that's kind of it for our thing, other than the few examples I'm going to be doing on the next page of showing algebra tricks. That is the expectation of what L'Hopital's rule is like. All right, so here are some final examples I have of functions which don't look like the classic indeterminate forms, but can be algebraically simplified. So let's start off with G here. I'm going to plug in 0. I get 0 times ln of 0. ln of 0 is negative infinity. So this is 0 times some version of infinity. So this is indeterminate, but it's not in a way that we have a top and a bottom so that we can use L'Hopital's rule. So we're going to use some algebra to simplify this. So when you have things that are multiplied instead of things that are divided, right? We want things divided so we can use L'Hopital's rule. We have things that are multiplied. So we use this idea of like, instead of dividing, you can multiply by the reciprocal. So instead of multiplying by the reciprocal, you can divide. We're gonna do that division trick, but in reverse. So we can do this. Check this out. And once you see it a couple times, you're like, oh yeah, I can do that trick. You'll know the trick after you see it a few times. So the limit stays the same. And instead of times, I'm going to do a divided by. But I have to divide by the reciprocal, otherwise it's not going to be equivalent. So there we go. We have an example of a function ln x divided by 1 over x. And if I flip and multiply 1 over x, I just get x over 1. So these are equivalent. You can imagine that this and this are the same just because of how we simplify these fractions by 1 over x, but we're doing it in reverse, right? We're complicating this function so that it looks like a fraction. Now when we plug in 0, well, we still get ln 0 on the top. And now we have 1 over 0 on the bottom. So the top becomes negative infinity, and the bottom becomes some version of infinity plus or minus infinity. So that means we can now use L'Hopital's rule. Infinity over infinity is one of the versions that we can use L'Hopital's rule. All right, so we're going to use L'Hopital's rule. L'Hopital's rule. The derivative ln x is 1 over x. Derivative of 1 over x is negative 1 over x squared. And if you need a refresher of that, the derivative of 1 over x is the same as the derivative of x to the negative 1, which is negative 1 x to the negative 2, or negative 1 over x squared. Now, you're welcome to try to plug in 0 directly here and try to figure what it is, but it would be nice if you simplify this first. This is a very complicated looking function. So let me just simplify this before I try to plug in 0. It's just going to make my life so much easier. So I'll go back and do the flip and multiply thing. So I get the top thing times the reciprocal of the bottom. And this becomes negative x squared over x, which is, well, negative x squared over x is just negative x. See how much easier it is now when I plug in 0? When I plug in 0, I just get negative 0, which is just 0. So that means the original limit is also equal to 0. So anyway, so that's another kind of important thing to think about, is that, sometimes simplifying is going to get you very far. All right, so let's look at example H. We have the limit as x approaches 0 of x to the x. And when I plug in the 0 directly, this becomes, well, it becomes 0 to the 0. And 0 to the 0 is one of our indeterminate forms. So we're going to be able to use L'Hopital's rule as long as we simplify this in some way to make it look like 0 over 0 or infinity over infinity. So how do we simplify an exponential to look like a division problem? Well, this is exactly what we did with what was called logarithmic differentiation. And I actually tried to call it logarithmic simplification because I really think that's a better name. We're not actually doing a derivative with our logs. We're just simplifying the function with logs, and then we can take the derivative. Similarly, we're going to be simplifying this function using logs and then finding the limit. So it is maybe logarithmic limitation. I don't know what it is, right? We're using logs to simplify this thing. Just so that I can make it easier to explain, I'm going to make this into an equation just so that it's easier to sort of see what we're doing on both sides. So I'm going to say whatever our answer is, it's going to be y. So if I can find the value of y, then I find the value of this limit. So I'm just making a variable equal to my answer, just so it's going to be easier to explain what's going on here. So I'm going to be using logarithms to simplify this thing. So I'm going to take the logarithm of the left-hand side, and I'll take the logarithm of the right-hand side. Logarithms of both sides, right? So on the left-hand side, we have natural log of y. On the right side, limits are really well behaved with the functions. You can move functions in and outside of limits. The only thing that's happening is x is changing. ln doesn't do anything, so I'm going to write it on the inside like this. We did that before, where we just said, hey, we're just going to be plugging in 0 into x anyway, so it doesn't matter where the ln is. All right, so why is this helpful? Because this is ln of a thing raised to a power, And we know that we can use those log properties, those log rules of simplification to bring that power down. So this would be x times ln x. Right? Remember the x from here comes down in front, right? That's one of our ways of simplifying logarithms. So we have ln of y is equal to this limit right here. Up here. So we get ln y is equal to this limit here. But that limit we just did. This is the answer from part G. Remember, limit as x approaches 0 of x times ln x was the example I just did before. So this is equal to 0 from part G right up there, right? So from part G, we just did the fact that the limit is equal to 0. So ln y is equal to this limit, but the limit is 0, so that means ln y is equal to 0. Now, our goal was to find y. Remember, y was the thing that we wrote down as equivalent to our answer. So all I have to use now is algebra. I'll do the exponential of both sides. Exponential of log y is just y. E to the 0 is 1. And so I know my limit, which was set equal to y. This limit here is equal to 1. All right, so there's an example of using logarithms to simplify an indeterminate limit. Okay. So letter I, we have another limit as x approaches 2. Once again, immediately I just try to substitute, see what I get. When I substitute 2, I get 1 over 2 minus 2 minus 4 over 2 squared minus 4, which is 1 over 0 minus 4 over 0, which is some version of infinity minus some version of infinity. So we have an infinity minus infinity kind of situation. So we're going to try to see if we can simplify this so that we can use L'Hopital's rule. Infinity minus infinity is one of our indeterminate forms. Okay, so how do we simplify this? Well, we simplify this just by combining things together. We need one fraction with one thing on the top, one thing on the bottom, 0 over 0, or infinity over infinity. That's how we use L'Hopital's rule. So we'll just use some algebra here to simplify this. We need some common denominators. So I might want to remind you that x squared minus 4 is just x minus 2 times x plus 2. If you factor it. So we know that the bottom, if you multiply the bottom and the top by x plus 2 for the first fraction, you'll end up with the same denominator for the second for the second fraction. So I'm going to multiply top and bottom of the first fraction. That will give me the minus. X plus 2 over x plus 2, x minus 2, and then minus 4 over that same denominator. In fact, I don't need to write the denominator twice, because I can just write them all over the same denominator, right? So I can just write this whole thing, top part over the same denominator minus the other top part over the same denominator. Okay, so this is what we have, and then I'll just write out what this is. X plus 2 minus 4 is x minus 2. And the bottom is just x minus 2, x plus 2. Hey, look at that. There is an x plus 2, or x minus 2, which is common in the top and the bottom. So I'll divide those out. And that gives me the limit as x approaches 2 of 1 over x plus 2. And now when I use direct substitution, I get 1 over 2 plus 2, which is equal to 1 over 4. So 1 over 4 is the value of the limit. All right, so 3 different ways of simplifying things. that are a determinant to hopefully be able to figure it out. This one, we didn't even need to use L'Hopital's rule. Sometimes you will. This one, once we simplified it, we could just plug it in directly. All right, my last example before our video ends. Just a reminder, here we go. 1 over x minus 2 is going to go to, when I plug in 2, goes to 1 over 0. This becomes 3 over 0. So we have a infinity minus infinity kind of thing. So we're going to, once again, do the same thing we did before and add the fractions together. I'm going to multiply this one by x plus 2 and x plus 2, like that and like that. And so I'll get a common denominator. So I'm not showing all the same steps as before because we just did them. So the common denominator is going to be x minus 2, x plus 2. This first numerator is going to be x plus 2, and then it's minus 3. So I just changed the 4 from the previous problem to a 3 on this problem. So it looks almost exactly the same, but instead of a minus 4, we have a minus 3. So this is what we had before, and this we have right now. You can see they're identical except for instead of a minus 4, we have a minus 3. Okay, so what do we get here? So this becomes limit x approaches 2, and x, this is a plus 2. X plus 2 minus 3 is x minus 1. And this is x minus 2, x plus 2. All right, well, we don't get the nice division here. So we're going to just try plugging in 2. 2 minus 1 is 1. I'll just write 2 minus 1 here. And then we get 2 minus 2 and 2 plus 2. 2 minus 1 is 1. And we get a 0 times 4. But 1 over 0 is plus or minus infinity. All right, so this limit, depending on which side, if you come from the right side or the left side, is either going to be positive infinity or negative infinity. All right, so those are my examples for using L'Hopital's rule. Hopefully that was all helpful, and you will reach out if you have any questions or want some more practice. I hope you have an enjoyable day.